Hello, this is Alparslan from University of Delaware, and I'm a PhD candidate there. And this work was a collaboration between Gazi University, Turkey, and Chalmers University of Technology, Sweden. I work with Dr. Sahin and Dr. Butun on this work. Okay, so I will explain the problem statement and background and methodology that we are using, and I'll explain the design, and I'll present the results and conclusion. So the problem statement is, as you know, the compiler optimization is one of the essential work in the computer science that we are trying to optimize, and it's very competitive that people are working on the fragmentation of seconds, to improve the compiler optimization. It's important. Why? Because we are using compiler optimization in games and simulation related softwares like rendering and then scientific calculations and high performance computing. So if you want to get some great running programs, we need to focus on compiler optimization. And the optimization process itself a big search problem, and it's considered NP hard. And it's always, welcome to code in an efficient way, which will be fast runner, but the focus is here in compiler level, how we can improve the running time faster. So like we gave the game example, right? It's important because when you develop a game and when you compile it, like millions of people are using the same code. If, local projects, used by 5-10 people, you may not consider doing the compiler optimization and spend more time. But if you consider one product is being shipped to millions of people, you may want to use some compiler optimization in your product. And again, for simulation software, high performance computing, the fraction of seconds is an important metric to consider and spend more time on compiler optimization. Like as a background study, Cavazos et al. Developed a genetic algorithm-based approach to auto-tuning dynamic compilers, internal inlining heuristic for Java. Also, Cavazos explored the viability of developing intelligent compilers. He's one of the pioneer in these intelligent compiler area, John Cavazos. And then he was focusing on replacing hand tuning algorithms for the compiler optimization with auto-tuning features, and then concluded that machine learning is an excellent solution to solve optimization problems. So the AI boosted compiler optimization is a really important concept. And then Plotnikov also presented an automatic tool which uses genetic algorithm core to search the compiler optimization parameters. And then Agako also uses smart and genetic algorithm to do compiler optimization techniques. And then Lin et al. Showed compiler flag selection with genetic algorithms with pool of 128 flags with promising results. And again, Belal implemented a genetic algorithm to select optimization level of compiler flags and then perform some optimization. So here what we are doing is we are using GCC for compiling our programs, but GCC has an option to provide compiler flags. So you can configure GCC with hyperparameter optimization, and we take advantage on that just using the available tool. And then we try to change the GCC flags randomly or based on genetic algorithm. And genetic algorithm requires a good heuristic algorithm to judge the child's and then population results. So I will explain them in the next following slides. And then once we compile the benchmark programs, we get the baseline with compiling by default GCC. And then we change the hyperparameter optimization, and then we get the measurements, and then we find the best compiler flags for a given program. So GCC has some default flags like 00, 01, 02, 03. So there are pros and cons, like if you are using 00, the code size is increasing, but compile time is kind of reducing, execution time is increasing, memory usage is less. So these are the default compiler properties. And then in this study, we are using multi-agent system to implement our ideas. Let me explain briefly what's the architecture. We are using BDI, which is a software model developed for programming intelligent agents. And then belief here represents the informational state of the agent about the world, about the agents, and about the interaction between agents. Anything related to the domain is in this belief. And then rule set that we are saying, hey, if you see this kind of thing, do this, do that. These kind of rules also fits in the belief. And then desire, actually here in the goals, goal is a desire. And then the desire represents the motivational state of the agent. Like, for example, if you are writing a shopping agent, it's kind of finding the cheapest price. In our case, we are writing a compiler optimization agent that it should find the best execution time for a given software. And then plan is the sequence of action which an agent takes. And then events, you see these goal events, condition events. Like, these events are the triggers for reactive activity for the agent. Like, an event may update some belief, and then the goal, the state of the agent, those kind of communication. And then this is our abstract design that we project to build some agent clusters, in cloud, that there could be compiler as a service system in cloud, which consisting of these agent frameworks and agent clusters. And then in each agent cluster, right now we have two different agents, which one of them is the random search agent, which is customized for doing random search in that search space to randomly generate these bit strings. And then these bit strings are translated to GCC compiler flags. In each flag here, like 1 means turned on, 0 means turned off. And then based on the location, it will specifically controls a GCC flag. And then these random search agent randomly generates these bit string, and then we compile the program with these compiler flags, and then we get the runtime performance. And then we evaluate that again, the agent evaluates them again, and then generates another random. And here, these genetic algorithm uses genetic algorithm with given bit strings. In each bit string divided by 2, and then crossover with other childs, and then generated new bit strings is being evaluated by the genetic search algorithm. And then they are communicating with each other, passing information, saying, hey, I find these, it's much better. And then feed, like, these random agent can feed the genetic algorithm agent with the optimized flag options. And then genetic algorithm has much better idea. So considering if you run genetic algorithm without any input, it will start from the baseline, and then the improvement would be slow. But if you feed some improvements as a starting point with genetic algorithm, the crossovers would be much meaningful, and then the genetic algorithm would be finding the optimized result faster. And then we are using the performance evaluation with the runtime timing, that we inject the start timing in the beginning of the program, the benchmark program. And at the end, we are getting another time option, and then the result would be calculated at the end. And we are just using a desktop system to evaluate these. It's just the Intel i7 desktop to evaluate these benchmark programs. And the result is we find that both our random agent and then the genetic search agent, which random search and genetic search, genetic algorithm search has a much better result, runtime execution result. And here we see we generated a random number between 0 and 1. And these are the midpoints, decision points saying that the flag should be on or off. And we consider these midpoints 0.12 and 0.9. And these are the results for that random search with different midpoints to deciding to turning on or off for the given compiler flag. And these are the our benchmark soft benchmark programs. And then as you see, like they're all over, like the 1 is the baseline. And then the most we achieve is the 100% of the runtime. And then this is the genetic algorithm search result. Again, the baseline is 1. And we were able to do improvement for all benchmark programs. And then with these population size and child size optimization parameters has the best result for the genetic algorithm. And then this is what happens when we provide some initial population based on the random search, and then the genetic algorithm is the orange, and then random plus genetic algorithm is the yellow, which has the better results. And then as a like metric here, the 1 is the baseline, and then the greater number is the greater result that we have. And if you see, these are randomly provided some initial population to genetic algorithm has the best runtime metrics, except this one. For these L3 benchmark, the genetic algorithm found the best result. But in overall, what we learned from here is even, you know, we have GCC already doing the optimization in compiler level, but once we take over the compiler optimization parameters, you know, saying, hey, we are gonna provide you these compiler parameters that we can optimize the given software better than GCC, because GCC is just compiling with the default options. And then also random search finds some promising results, and genetic algorithm finds promising results. But when we feed the genetic algorithm search with an initial findings of random search, would perform the better. And then these multi-agent framework is designed in a modular and scalable way, which can be deployed to cloud, and then which we can easily add new agents, saying that, you know, the traditional compiler optimization methods, like the checking the code sequence and then finding that code elimination, or basic block scheduling, or low-level assembly optimization, these can be plugged easily to these agent framework. And these system can be performed on cloud level, which, you know, faster than the local compile environment. In parallelly, we can do multiple compiler optimization. So as a futuristic work, we would be planning to do that. And based on collected metrics, the machine learning algorithms can be performed, and then do some auto-tuning as a future work as well. And I just want to bring to acknowledge this guy, John Cavazos. He was my mentor at University of Delaware. which has a kind of like great ability in compiler optimization and then work, but we lost him in 2018. So just to respect him, I just bring this to your attention. And any question related to these work?
I might have a question, Alparslan.
Okay,
so
sure.
we are optimizing the compilers. It's really good. Code optimization and compiler optimization is really good for us, as you have shown with the results. But what's the trade-off here? In what expense we are gaining this benefit?
The trade-off is time. As I mentioned, the compiler optimization is a search problem, and then this search requires time. And the domain is infinite. You can consider that way, like how much time you want to spend. So if you are doing your desktop projects, your college projects, you may not consider doing compiler optimization. But again, as I mentioned, if you are developing a game project for PlayStation, which will be shipped to millions of people, you may want to spend a week or a month to find the best optimized software, the compiler. The expense is time here, the concern.
It's also relevant to stall elimination, right?
Yeah, like in my one of the other work, I did the compiler of basic block scheduling to eliminate CPU level stalls in the code. So the CPU would consume the assembly instructions much faster. But in this work, we are just controlling GCC in a higher level that try to compile the software with whatever GCC offer us.
I understand.
But again, with this multi-agent system architecture, that all low-level compiler optimizations and code optimizations can be easily applied to these agent framework. That's one thing we need to consider in our future work.
Perfect. I wish you good luck in your next endeavors. And thanks for your presentation again.
Thanks for listening to me, guys. Have a good day.